So the question is, how do you decide what energy of X-rays to use to create the image? I think that's fundamentally the question, right?
Yeah, yeah.
Yeah. And it, it's a terrific question. And so, but we can answer it with a couple of examples. If I used X-rays that were all low energy X-rays, say they were 30 keV X-rays, because I
Mm-hmm.
only had that many volts. When I shine my X-ray source at the patient and look at my detector, I would see nothing,
Mm-hmm.
right? So there's no point in using those X-rays, right?
Right.
Let's go to the opposite end. If I now use gamma rays, which like are outside the X-ray spectrum, and they're like MeV energies, right?
Mm-hmm.
And so those photons
Mm-hmm.
have so much energy that like 99% of them pass through the patient,
Right.
right? You can actually make an image with that because some of them got absorbed,
Mm-hmm.
but most of them did not. And so what you see is a very low contrast version of an X-ray image when the energy is too high.
Why is it low contrast? Like, what makes it low contrast?
Because the fraction of photons that get through in air versus those that get through the patient isn't that much different, right? So
Okay.
like maybe the patient only absorbs 1% of all of those gamma ray photons.
Okay. I
And so it
see.
gives you a very small contrast dynamic range.
I see.
Uh,
Mm-hmm.
and then as we go in between, let's let's pick the spot, the energy at which half of the photons get absorbed and half of them get through to the detector.
Mm-hmm.
That
Yeah.
makes sense, right?
Right.
Because
Yeah.
now we fairly efficiently used our radiation source, which is the X-rays,
Uh-huh.
hit the patient and create an image on our detector that has a high dynamic range between, say, air and
Mm-hmm.
soft tissue,
I
bone
see.
and soft tissue. So that's
I see.
kind of how it was figured
So
out.
it's to maximize the contrast between the different tissues.
Correct.
Okay.
And then you can actually compute using very sort of complex Monte Carlo simulations for photons entering the patient, what the probability of their trajectory will be.
Uh-huh.
And then you compute how much energy is deposited in the patient and what their dose is.
Okay.
And essentially, you would like to also take that into account. So you want the highest signal to noise or contrast
Mm-hmm.
to noise between your target and the background
Mm-hmm.
per unit dose deposited in the patient. That would be the
Mm-hmm.
ideal thing to do. And
Right.
that's that actually changes depending on the size of the patient.
Okay. I
So
see.
as a patient gets bigger,
Mm-hmm.
say their BMI is like 32, they're a very large person.
Mm-hmm.
You need higher energy photons in order to get, a good fraction of them through.
Right.
And so you'll actually change the energy on your scanner if the person's big versus if they're little.
Mm, I see. Okay. And then the second question I had was related to sort of the mechanism for how these X-rays are generated. Because I kind of read before this lecture about like how X-rays are generated,
Mm-hmm.
and my understanding was that you have like the electrons like the metal, like the electrons get stripped from the metal,
Mm-hmm.
and then they hit the other metal, and then that. So I kind of had the idea that okay, the electron hits the other metal, and then it kind of removes the electron in the inner shell, and then the electron from the outer shell will then jump to the lower energy shell,
Right.
and then that jump will then cause X-rays to be X-rays to be released.
That's
But
correct.
then you said that in our like class we're not going to refer to this mechanism of generating X-rays.
Oh no,
um
I'm sorry if I said that,
or I
but
didn't understand, sorry.
yeah,
Yeah.
no, I mean that's the mechanism by which those K shell ejections and then the drop of the outer shell electron into the K shell gives a characteristic X-ray emission or line. And so there's spikes in the spectrum. But most of the spectrum, you know, let's go back to that. I think I probably have it here. Do you guys see my screen right now?
No, not right now.
You don't see it? Oh, 1 second. Let me share this. Okay. You see that?
Yes.
Okay, great. So this is the KeV, or the energy of the photons coming out of our X-ray tube, and the relative number. These lines, I mean, there's a lot of photons coming out at these energies because those are the K shell ejections, right? So they're called the characteristic emissions. However, they only make up a small fraction of the photons that we see. The photons that are in this energy level, what happens is the electron, when it hit the target, had this Compton scattering. And it was that Bremsstrahlung radiation in which the electron does a really hard turn, or it decelerates or accelerates, or goes under an acceleration or bending. And then when it does that, it emits a photon in the X-ray spectrum. And so most of the X-rays come from that process. Right?
I see.
That's the deal. And if it was all Bremsstrahlung and all the X-rays got out, you would see this straight line would just go up like this. But that doesn't happen. The low energy stuff that gets created gets filtered out.
I see. Okay.
Okay.
So that's why you see a low, like less of the low energy photons?
Correct, because they get filtered. They get filtered out. Yeah. Okay.
Yeah. Thank you.
Sure. So any other questions?